Welcome back. We're finishing up the 2.4 notes, and so we are on page 10 in the notes packet, and number 4 asks us to use algebra to identify the vertical asymptotes for each function, and then says we can verify that with the graphing calculator, which we may not have time to do on this video, that piece. But if I take a quick look at this particular problem, I want to start by factoring both the numerator and the denominator. And the numerator has a GCF of 4, which I'll remove that. And then I'm going to I'll finish up this numerator really quickly. I'll factor that trinomial as x plus 3 times x minus 2, and then that GCF of 4 remains. On the denominator, it also has a GCF, this time of x. So I'm just going to factor that out. And I'm going to notice that I have 4 terms remaining. And so a lot of times when there's 4 terms, I usually check to see if factoring by grouping will work. I'm going to actually go ahead and kind of continue factoring this by grouping just underneath here. I'm going to look at the first 2 terms and decide what GCF exists there, which would be, looks like x squared. And then if I look at the third and fourth terms, that has a GCF of 9. And because the third term leads with a negative, I'm also going to remove a negative. I'm going to just continue factoring this down below and place it in the denominator. I already put the GCF that we took out at the beginning of x. If I look now at this factoring by grouping, both of these portions have a GCF of x minus 2, so I'm going to remove that. And then I have x squared minus 9, which can factor as x plus 3x minus 3. So if I compare the numerator and the denominator, every factor on the denominator that is not repeated on the numerator is going to give us the location of a vertical asymptote. If you do have a factor that repeats, that is not a vertical asymptote. This is the location of a hole in the graph. So there's a hole at x equals -3, which is not actually what we're being asked to find, but I wanted to know why we were not using that answer. It looks like we also have a repeated factor of x minus 2 on the numerator, and so I can go ahead and reject that. That is yet another hole in the graph. So the factors that remain each give us a vertical asymptote. This one has a vertical asymptote at x equals 0, and this one has a vertical asymptote at x equals 3. Please notice that these are equations because vertical asymptotes are lines. For number 5, this one will have vertical asymptotes where the denominator, the factors on the denominator, are equal to 0. So I want to go ahead and see where the sine of x would equal 0, which we actually kind of explored a little bit on some previous problems when we were looking at tangent. And we said that sine of x is the height for each of the ordered pairs in our unit circle, which this would happen at x equals 0, pi, 2 pi, and so forth. We could also go in the negative direction and even have like negative pi, negative 2 pi. So how do we want to write that? I'm going to write this like this at x equals 0 plus pi n. You really don't need the 0 there. I don't know why I tend to write that starting point on there, but when the starting point is 0, it's not really needed. And I'm going to say that the n is an integer. And that way I can get all of the different options of pi. So if it's not a polynomial, we still can have vertical asymptotes. The most important thing is that those factors cannot be repeated on the numerator and the denominator. If they are, they're actually a whole and not a vertical asymptote. When we're looking at some properties of infinite limits, it might be helpful if we have a situation where we have one function, if I can highlight, one function where as we approach c along the x-axis for both f and g, but for f we're going to say that that limit is infinity or does not exist. So visually, we're approaching a height of infinity there at c, then that would be the location of a vertical asymptote, quite likely. Versus over here, for g of x, as x approaches c, we're approaching a height of L, where L is some constant. Okay, so we're going to say that L is a constant and C is a constant. And there are some properties that are true. Here's the first one. If I'm taking the limit as x approaches C and I want to add together f and g, and I will get infinity. Here's why. The limit as x approaches C of f is infinity, and for g is some constant. And I'm adding these expressions together, so I will add their limits together. And infinity plus a little bit more is still infinity. And again, we would say it does not exist, parentheses, infinity. For the second one, we have the limit for f, which was infinity, times g, and g was L. Now, if g is a positive, then we would end up with infinity times a positive, which is still just infinity. If if L is a negative, a positive times a negative would give us an output that's negative, but still very, very large. For this last portion, I want to do g divided by f. Well, g is some constant L, some number, 43, something like that, divided by f, which is approaching infinity. So if I have some small constant divided by an increasingly larger and larger and larger number, eventually I start to approach 0, because this grows faster on the denominator. And so you get small number divided by a huge number, like 43 divided by 17 trillion. And you start to get very, very small numbers that approach 0. So for these last two examples, we are not going to want to use a calculator, which can be a little tricky. These ones intentionally are a little bit tricky. And we're going to go ahead and see if we can figure out what these limits look like. First of all, this first one, although it has a trig function, does not match one of the special limits from 2.3 to 2. So we would want to use a different strategy. By the way, one strategy is to go ahead and substitute in a 0. That might be a little bit easier if we remember that the expression of cotangent is really cosine over sine. And since we're dividing by that, we could think of this as the limit as x approaches 0 of the expression x plus 2, and I'm going to recognize that when you divide by a fraction, it's the same as multiplying by the reciprocal, so sine over cosine. And I'm now going to substitute in the 0 and see what happens. So if I substitute in a 0, I get 2 times the sine of 0 divided by the cosine of 0. So this would be 2 times 0 over 1, or 2 times 0, which is 0. And so substitution can still be a valid method. In fact, it's probably, in most situations, a really good place to start. For number 7, I want the limit as x approaches 0 from the left, which is a little bit unusual, of x squared minus 1 over x. I'm going to use a very graphical approach here because approaching from the left, that's pretty visual for me. So I'm going to actually draw a graph of each of these. I'm going to think of this as the limit as x approaches 0 from the left of x squared minus the limit as x approaches 0 from the left of 1 over x. Well, I know what x squared looks like. This is just a parabola with its vertex along the origin. And so, and it's opening up. And so as I look along this, as I approach 0 from the left along the x-axis, my height is 0. So this would be 0. And then we are subtracting in between these limits. And 1 over x is the parent function for these rational expressions. We kind of mentioned that one earlier in the last video. And so 1 over x looks like this. And you should definitely memorize that. You will feel happy that you have that as a resource. And as I approach 0 from the left-hand side of this one, I am approaching negative infinity. Now I am subtracting a negative infinity. And so really this is like 0 plus infinity, and infinity plus any constant is still just infinity. And we're going to say that this limit then does not exist because it's approaching a positive infinity, which is not actually a numerical value that's finite and measurable. On the next page, there are some examples that you can do. And so I'm going to recommend that you pause the video and try them, and then I'm going to just display the answers. So when you're ready, you can go ahead and restart this. And I'm not going to go over these right now, but you can pause the video as needed in order to look more closely at any of these. And you can ask your teacher if you do have some additional questions on these. By the way, number 4 could be drawn many, many different ways. So this is just one possible solution. Again, if I'm going too quickly, just pause the video so that you can see the solutions a little bit more closely. Alright, and that is the end of the lesson from 2.4. And your assignment is to do 2.3 day 2 worksheet and 2.4 in your textbook.